is, I believe, the fourth video over convergence and divergence in BC Calculus, but it's the first video that we're officially calling part 2 of convergence and divergence. So in part 2, we're going to be looking at two more convergence tests, the comparison test and the limit comparison test. So both of these are useful when you have an explicit formula for a series that you're not quite sure what other route to take. Of all the different tests that we're going to end up having, these are kind of like the last resort, particularly the comparison test. Like if you have no other methods of going about determining convergence or divergence, then the comparison test can be useful to you. So we're going to start by writing out exactly how the structure of the comparison test works. So the comparison test says that given the sum from n equals 1 to infinity of an a sub n series, and then the sum from n equals 1 to infinity of a b sub n series, and the knowledge that a sub n and b sub n are both greater than or equal to 0. So this only works if their terms are all 0 or more. And a sub n is less than or equal to b sub n. So one of them has to have terms that are always smaller than the corresponding terms in the other series for n equals 1, 2, 3. So if the larger series, so that would be b sub n, converges, then that means that the smaller series, a sub n, also converges. So if the larger series converges, the smaller series converges. But if we look at it the other way around, if we can show that the smaller series diverges, then that means that the larger series also diverges. So this can be used in either way. So you're probably wondering, well, how in the world is this supposed to be useful to me if one way shows convergence and the other way shows divergence? Well, you're not going to be given two series in one problem. You're going to be given a series, and so you may not be able to work with it the way that it is, but maybe it's similar to another series. And maybe the terms of it are always smaller than the other series. Well, if you can prove that that other series converges, then it means the original one you were working with converges. Or maybe the one you were given, it is similar to another series, but all of its terms are larger than this other series. Well, if the smaller one that you're comparing it to diverges, then that means that your original guy would diverge. But you kind of have to know some helpful and useful series that you can kind of look at and immediately tell are going to converge or diverge. Otherwise, you're just creating a whole lot more work for yourself. This comparison test, though, we're actually going to use it to prove from, I don't know how many videos ago, sometime in part 1, when we discussed the sum from n equals 1 to infinity of 1 over n and the fact that that series diverges. So that's called the harmonic series. It's just a special name for that 1 over n series. And I told you back when we were looking at the nth term test that 1 over n would diverge. The nth term test was inconclusive for us, but I told you that eventually we would figure out why it was that 1 over n diverges, when you would think, since the terms are getting smaller, that this series should converge. So we have 9 terms of this series written out for us. You can see that they're getting smaller, so logic would tell us you would think that that sum would converge to a specific number then. However, that's not the case. If we kind of group it, I'm going to compare it to the terms for another series that I'm going to write out. So 1 aligns with 1, 1/2 aligns with 1/2. Now, if I take 1/3 is more than 1/4, and 1/4 is the same as 1/4. So these 4 terms align to these 4 terms. Well, these 4 terms add up to a total value of 2, right? Then 1/5 is more than 1/8. 1/6 is also more than 1/8. 1/7 is more than 1/8. And 1/8 is the same as 1/8. So these 4 align to these 4, which add up to a total of 4/8 or 1/2. If I was to then do the next grouping of terms, it would actually take me 8 terms, and I would compare them to 1/16, all the way from 1/9, 1/10, 1/11 here in this series. They would all be less than 1/16. If I take 8 of them and make 8 1/16, those would add up to another 1/2. I'm going to continue to be able to add 1/2 and another 1/2 and another 1/2. I'm just going to have to use more and more terms to lump together to make a value of 1/2 in this red series that I've written out. And as I previously said, the terms that they align to are all greater than or equal to the ones that I've written here in red. So this would be my A sub n series because it is smaller than the 1/n series. A sub n is less than or equal to B sub n for all of the corresponding terms. I have shown that my A sub n series diverges based on my work there because I'm going to keep adding lumps of values of 1/2. So it's going to continue to grow by 1/2 and 1/2 and 1/2. It's just going to stretch out the intervals before I can lump those 1/2s together. Therefore, the B sub n series, which is the sum from n equals 1 to infinity of 1/n, also diverges by the comparison test. Now, it's really very rare that you do a comparison test like this by specifically actually writing out values. Like, I never gave you a formula for this A sub n series. I just aligned it to some terms that I knew were going to lump together and would diverge. Most of the time, you want to compare it to an actual equation. So here's an example of one that we can use to show convergence. So we would be given the sum from n equals 1 to infinity of 1/2 to the n plus n. So just to look at some terms of it, if I substitute in starting with n equals 1, I would get 1/3 plus 1/6 plus 1/11 plus 1/20, and so on. And you notice that your terms are decreasing, so we would hope that this would be one that would converge to a particular sum. But as we saw with 1/n, just seeing that the terms decrease is not an automatic given for the fact that the series would converge. Now, I can compare that to a very similar series, the sum from n equals 1 to infinity of 1/2 to the n. Because this little plus n here, all that does is make the denominator larger, which makes the overall fraction for each term smaller in value than if I had just used 1/2 to the n. 1/2 to the n is bigger or equal to my original guy there. So just so you can see, some terms for this, if I started with n equals 1, it would be 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. And each of these that align, you notice that the row across the bottom, each of those is a larger value than the one that it corresponds to in my original series. 1/2 is more than 1/3, 1/4 is more than 1/6, and so on. Now, saying the sum from n equals 1 to infinity of 1/2 to the n, there's actually another way that I could write that. I could write that as the sum from n equals 1 to infinity of 1/2 to the n. Because 1 to the n is always just going to be 1. So I can write it either way, the way that it was originally written or the way that I just did. Writing it like this, though, helps me notice that that's a geometric series. That's an r to the n series there. Plus, if you look at the terms, you notice that there's a pattern, and the common ratio is 1/2, which is less than 1. So what we learned from the ratio test is that this series, the sum from n equals 1 to infinity of 1/2 to the n, would converge by the ratio test. We also notice that those terms are all larger than 1 over 2 to the n plus n. So this is our smaller series, that's our a sub n, and this is our larger series, our b sub n. So a sub n is the sum from n equals 1 to infinity of 1 over 2 to the n plus n. And then b sub n is the sum from n equals 1 to infinity of 1 over 2 to the n. And a sub n is always less than or equal to the terms in b sub n. And b sub n converges, therefore a sub n converges. This sentence that I've kind of filled in here, starting with the a sub n equals, that really is my statement that I need to make at the end of every sort of problem like this as to how I determine convergence. And it would be even better if I added by the comparison test. Now, I do actually have to show that work of how I determined that the b sub n series, the 1 over 2 to the n, converged by the ratio test. So I would need to show all of this stuff right here for how I knew that the b sub n converged. I can't just say that it converges, and so therefore by comparison, a sub n converges as well. You have to actually prove that the one you say converges really does converge. Okay, so that's the comparison test. I'm going to end this first video right there, and then we will make a second video for part 2 that is all about the limit comparison test.